For over 6 million years, human evolution moved like a glacier. Slow, grinding, almost imperceptible. Our ancestors came down from the trees. They learned to walk upright. Their brains grew, bit by bit, millimeter by millimeter. A few thousand years might pass between meaningful changes. 100,000 years for a new stone tool designed to spread across a population. Evolution doesn't rush. It experiments, slowly, patiently, across timescales that make human lifetimes feel like heartbeats. Then, around 100,000 years ago, something changed. Something broke. The rules that had governed human development for millions of years suddenly stopped applying. Our ancestors began evolving faster than they ever had before, not just biologically, culturally. They started creating art, carving beads and jewelry, burying their dead with ceremony, developing sophisticated weapons, trading materials across hundreds of miles, using symbols that represented abstract ideas. Within just a few tens of thousands of years, they went from being another interesting primate to becoming us. This is one of the deepest mysteries in all of human history. The Great Acceleration. The moment when everything changed. Scientists call it the Upper Paleolithic Revolution, or sometimes the Great Leap Forward. But those terms don't really capture how strange this is, how unprecedented, how completely it violates everything we know about how evolution normally works. Species don't just suddenly accelerate like this. Change is supposed to be gradual, incremental, spread across geological timescales. But our ancestors didn't follow the rules. If you're listening to this to fall asleep, that's exactly why I make these. So maybe subscribe and drop a comment telling me where you are and what time it is right now. I love reading them. Sydney at sunrise, Seattle at midnight, Seoul in the afternoon. All of you listening to the same story across every time zone on Earth. The puzzle has haunted anthropologists for over a century. What happened? What changed? Was it something in the environment? Did climate chaos force our ancestors to adapt or die? Was it biological, some genetic mutation that rewired the human brain? Was it social? A critical mass of population that enabled ideas to spread and build on each other? Or was it language? The sudden explosion of complex speech that let humans share knowledge in ways no species ever had before? The honest answer is nobody knows for certain. We have theories, good ones, compelling ones. But the truth is we're trying to reconstruct the most important transformation in human history from fragments of bone and stone scattered across 100,000 years. It's like trying to understand a symphony after hearing only 3 notes. Picture the world 150,000 years ago. Africa is vast and varied. Deserts, savannas, forests, mountains. Small groups of anatomically modern humans are scattered across the landscape. Maybe 10,000 of them total, maybe fewer. They look like us. If you saw one walking down the street in modern clothes, you probably wouldn't notice anything unusual. Their brains are the same size as ours, the same basic structure. But something is different, something crucial. They make tools, yes, but the same basic stone hand axes their ancestors made for hundreds of thousands of years. They hunt, gather, raise children, form social bonds. They survive, but they don't innovate much. Their culture changes but slowly. A new tool design every 50,000 years. Technologies stay localized, don't spread. There's no art we can recognize, no decoration, no clear evidence of symbolic thinking. Then, around 100,000 years ago, the archaeological record begins to shift. Subtly at first, a few carved beads here, some ochre pigment there deliberately shaped, then faster, more sophisticated tools, evidence of long-distance trade networks, elaborate burial sites showing clear ritual behavior, cave paintings that make your breath catch in your throat because they're beautiful, unmistakably intentional, undeniably human in a way that earlier artifacts just aren't. By 50,000 years ago, the transformation is complete. Our ancestors have become unstoppable. They're adapting to every environment on Earth. They're crossing oceans, reaching Australia. They're surviving in frozen tundra and tropical jungles. They're creating art and music and religion and science, the foundations of everything that would eventually become human civilization. But what triggered it? What lit the spark that turned slow-evolving primates into the most adaptable, creative, dominant species the planet has ever seen? That's what we're here to explore. The theories, the evidence, the competing ideas that scientists argue about in conferences and journals. We're going to travel through time, back to the crucible where modern human consciousness was forged. Back to the moment when everything changed. When we became truly, fully, unmistakably human. The journey starts now. Close your eyes, let your breathing slow, and come with me into the deep past where the greatest mystery of human existence is waiting to unfold. Before we can understand what exploded 100,000 years ago, we need to grasp just how slowly everything had been moving before that moment. And I mean slowly, glacially, almost impossibly slowly by modern standards. Let's go back, way back, about 2.5 million years ago, when the first members of our genus, Homo, appeared in East Africa. These weren't humans as we'd recognize them. They were smaller, with brains about half the size of yours. But they could walk upright, use their hands with precision, and most importantly, they could make tools. Those first stone tools were crude. Take a rock, smash it against another rock until you get a sharp edge. That's it. No design, no planning, just percussion flaking until something useful emerged. But it worked. Those simple choppers could butcher animal carcasses, strip bark from trees, dig for roots. They gave our ancestors access to new food sources, new possibilities, and then, for hundreds of thousands of years, almost nothing changed. You have to understand how strange this is. Imagine using the exact same iPhone design for not just years, but for 300,000 years. The same model, the same interface, generation after generation after generation. That's what our ancestors did with stone tools. The technology barely evolved. Sure, individuals got better at making them through practice, but the fundamental design remained frozen in time. Then, around 1.7 million years ago, something shifted. Someone, somewhere in Africa, figured out how to make something better. Not by accident, but through deliberate planning. They created what archaeologists call the Acheulean hand axe. Picture a teardrop-shaped piece of stone, carefully flaked on both sides to create symmetrical edges that meet in a point. It fits perfectly in the human hand. It's beautiful in its way. Elegant. You can use it to butcher meat, chop wood, dig, scrape hides, maybe even throw it at prey. It's the Swiss Army knife of the Stone Age. This was a massive cognitive leap. To make an Acheulean hand axe, you need to visualize the finished tool before you start. You need to understand three-dimensional geometry. You need patience, precision, and the ability to correct mistakes as you go. These tools took real skill to produce, and then, for the next 1.5 million years, that's what we made. The same hand axes, over and over, generation after generation. The same basic design, spreading from Africa to Europe to Asia, carried by migrating populations of Homo erectus and their descendants. Archaeological sites from England to India show essentially identical hand axes, spanning more than 1 million years of human prehistory. Think about that. 1 million years. The same tool. Your ancestors could have picked up a hand axe made by someone 50,000 generations removed and immediately known what it was for and how to use it. Technology had become standardized, yes, but it had also become frozen. During this immense stretch of time, physical evolution was happening, but so slowly you'd need thousands of generations to notice the changes. Brain size was gradually increasing. Homo erectus started with brains around 900 cubic centimeters, about 2/3 the size of modern humans. Over 1,000,000 years, that slowly crept upward. 950 cubic centimeters, 1,000, 1,100. Each increment probably took tens of thousands of years to become established in the population. Bodies were changing too. Homo erectus had already figured out how to walk and run efficiently on 2 legs, but their proportions were still different from ours. Shorter legs relative to their torsos, thicker bones, more robust builds. Over hundreds of thousands of years, natural selection refined these traits. Lighter bones developed in populations that ranged widely. Longer legs in groups that lived in open grasslands. But these changes were incremental, subtle, a slightly different angle to the pelvis here, a fractionally larger brain case there. Nothing dramatic, nothing revolutionary, just the slow, grinding work of natural selection, testing tiny variations generation by generation, keeping the ones that worked fractionally better than the alternatives. Life during this long silence was hard in ways we can barely imagine. Small groups, maybe 20 to 40 individuals, wandering across vast territories in search of food, following animal migrations, tracking seasonal patterns of plant growth, always moving, always searching. They had fire, probably. Evidence suggests Homo erectus learned to control fire at least 1,000,000 years ago, maybe earlier. That was huge. Fire meant warmth, protection from predators, the ability to cook food and make it more digestible. But beyond that, their lives would have seemed almost alien to us. No permanent settlements, no agriculture, no domesticated animals, just the endless cycle of finding food, eating, sleeping, reproducing, and teaching the next generation the same survival skills your parents taught you. The archaeological record from this period is sparse, and what we have is mostly stone tools and occasional bone fragments. There's almost no evidence of symbolic thinking, no art, no ornaments, no burial practices that suggest they conceived of death as anything other than the end of movement. Their tools were functional, not decorative. They made what they needed and nothing more. Some populations of Homo heidelbergensis, who appeared around 700,000 years ago, might have been developing the cognitive machinery for symbolic thought. Their brains were approaching modern human size. They built sophisticated wooden spears, perfectly balanced for throwing, found preserved in a German bog. This suggests they could plan ahead, coordinate hunts, teach complex skills. But if they were making art or jewelry, if they were painting or singing or telling stories, they did it in ways that left no trace. No cave paintings, no carved figurines, no beads or pendants, just tools and bones and the faint impression of footprints in ancient mud. For millions of years this was human existence, survival, reproduction, the gradual accumulation of tiny improvements in tool-making and hunting techniques. Nothing dramatic, nothing revolutionary, just the slow, patient work of evolution, testing and refining and occasionally discarding failed experiments. Different human species came and went during this long silence. Homo erectus spread across the Old World and eventually went extinct. Homo heidelbergensis evolved in Africa and Europe, then split into different populations. Some headed north and would eventually become Neanderthals. Others stayed in Africa and continued evolving toward what would eventually become us. But all of them were stuck in the same pattern. Stone tools that changed only incrementally over hundreds of thousands of years. Brains that grew larger but didn't seem to produce fundamentally new ways of thinking. Social groups that remained small and simple. Technologies that stayed basic. The question that should haunt you is why? Why were our ancestors stuck for so long? They had large brains, some approaching or even matching modern human brain size. They had sophisticated bodies adapted for endurance running and precise hand movements. They could make complex tools and control fire. They could communicate, probably through some form of proto-language. But something was missing. Some spark that hadn't yet ignited. Some combination of factors that hadn't yet aligned. For millions of years, human evolution was writing a story of almost imperceptible change, bodies adapting slowly to different climates, brains growing gradually larger, tools improving at a pace that would make a glacier look speedy. And then, in what amounts to the blink of an eye in evolutionary terms, everything changed. The long silence ended. The explosion began. But before we get to that transformation, you need to understand one more piece of the puzzle, the crisis that nearly ended the story before it could really begin. Because sometimes the worst disasters create the conditions for the greatest transformations. And what happened around 900,000 years ago would set the stage for everything that followed. Something extraordinary happened around 100,000 years ago. Not everywhere at once, not in a single revolutionary moment, but gradually, unmistakably, human behavior began to transform in ways that had never happened before in millions of years of evolution. Archaeologists call it behavioral modernity, the emergence of distinctly human capabilities, art, personal ornamentation, sophisticated technology, symbolic thinking, the stuff that makes us feel fundamentally different from every other species on Earth. But there's fierce debate about when exactly this happened, how fast it happened, and whether it even makes sense to talk about a single transformative moment. Some researchers argue for a sudden cognitive revolution, a genetic mutation or neurological rewiring that switched on modern human consciousness like flipping a light switch. Others see a gradual accumulation of cultural innovations, each building on the last until humans reached a threshold where everything changed. The truth, as archaeological evidence keeps revealing, is probably messier and more interesting than either extreme. Let's start with what we actually know. Around 100,000 years ago, archaeological sites in Africa begin showing artifacts that would have been impossible to find even 20,000 years earlier. Not just better versions of old tools, but entirely new categories of objects. Things that serve no practical survival function. Things made purely for symbolic purposes. Blombos Cave in South Africa gives us one of the most striking examples. 75,000 years ago, people were living in this coastal shelter, eating shellfish, hunting game, doing all the normal survival activities you'd expect. But they were also doing something else, something strange and unprecedented. They were collecting chunks of ochre, a reddish mineral rich in iron oxide. And they weren't just using it as pigment, they were engraving it with geometric patterns. Cross-hatched lines, carefully etched in parallel rows, abstract designs that required planning, precision, and hours of focused work. These aren't random scratches. They're deliberate patterns, repeated across multiple pieces of ochre. Somebody spent significant time creating these designs. But why? Ochre doesn't help you hunt better. Geometric patterns don't make you warmer or safer. The only explanation that makes sense is that these objects meant something. They were symbols, representations of ideas that existed in someone's mind and needed to be made real, permanent, shareable. Think about what that requires cognitively. You have to be able to hold an abstract pattern in your head, translate it into physical marks, and believe that those marks matter enough to be worth the effort. You need to think symbolically to understand that a line on a rock can represent something beyond itself. That's not just intelligence. Plenty of animals are intelligent. That's imagination, the ability to conceive of things that don't physically exist and make them real through creative action. But the ochre engravings are just the beginning. The same layers at Blombos Cave contain something even more remarkable, shell beads. Dozens of tiny marine snail shells, each one carefully perforated with a hole, worn smooth from being strung together and worn against skin. These are the earliest known examples of personal ornamentation in human history. Somebody collected these shells, probably from beaches miles away. They pierced each one using stone tools, delicate work that must have resulted in many broken failures before achieving success. Then they strung them together, probably on plant fibre or animal sinew that has long since decomposed, and then, and this is the really important part, they wore them. Against their neck or wrist or in their hair, they adorned themselves deliberately, transforming their appearance in ways that had nothing to do with temperature regulation or physical protection. Why would anyone do this? Imagine being that person. You wake up in your shelter, overlooking the coastline. You're going to spend the day doing the same things you've done 1,000 times before, gathering plants, checking fishing spots, repairing tools. But first, you put on your shell beads. You arrange them carefully so they're visible. You want people to see them. What are you communicating? Maybe status. Look at these rare shells I collected from distant beaches. Maybe group affiliation. We're the shell bead people, distinct from those other humans living over the next ridge. Maybe personal identity. This is who I am. This is what makes me different from everyone else. Whatever the specific message, the act of wearing jewellery represents a revolutionary shift in human psychology. It means you're thinking about how others perceive you. You're managing your social identity. You're participating in a system of symbolic communication where objects convey meaning beyond their physical properties. This is the foundation of culture as we understand it. Not just learned behaviours, but shared symbolic systems where meanings are collectively constructed and understood. The shell beads at Blombos Cave aren't just pretty ornaments. They're evidence that humans had developed the cognitive infrastructure for all complex culture that would follow, and once that infrastructure was in place, innovations started accelerating. Other sites from this period show new hunting technologies that represent quantum leaps in effectiveness. Hafted weapons, spear points attached to wooden shafts using plant resin adhesives and complex binding techniques. This might not sound revolutionary, but consider what it means cognitively. You need to understand abstract relationships between materials. You need to know that tree resin, when heated, becomes sticky and can bond stone to wood. You need to plan multiple steps ahead, gather materials from different locations, process them in specific sequences, and assemble them into composite tools. Then you need to teach this process to others. The complex hafting techniques appearing at multiple sites across Africa around 100,000 years ago couldn't have been independently invented at each location. They were being shared, passed down through generations, refined and improved through collective cultural transmission. The result was weapons that were dramatically more effective than anything that came before. A hafted spear lets you throw harder, hit from farther away, and strike with concentrated force that can pierce thick hide. It transforms humans from opportunistic scavengers into apex predators capable of taking down the largest animals on Earth. But perhaps the most telling evidence of behavioural change comes from long-distance trade networks. Archaeological sites from this period contain materials that could only have come from sources hundreds of miles away. Obsidian from volcanic regions, high-quality stone from specific quarry sites, marine shells far inland from any coast. This wasn't random movement of materials. These were systematic exchange networks, possibly maintained over multiple generations. Groups that never directly met were connected through chains of trade relationships. Knowledge was flowing along these networks too, tool techniques spreading from group to group, innovations being adopted and adapted by communities across vast distances. This is cooperation at a scale that had never existed before in human history. It required trust between groups. It demanded communication sophisticated enough to negotiate exchanges. It needed memory and cultural traditions to maintain relationships across generations. So was this truly a great leap forward? A sudden revolutionary transformation? The evidence suggests something more nuanced and perhaps more interesting. When you look at individual sites in isolation, the changes can seem dramatic. Blombos Cave has ochre engravings and shell beads in layers dated to 75,000 years ago, but the layers immediately below, just a few thousand years older, have neither. That looks like a leap. But when you zoom out and look at sites across all of Africa, the picture becomes more complicated. Some innovations appear early in certain regions, but don't show up elsewhere until much later. Personal ornaments appear at one site 90,000 years ago, but don't become common across Africa until 70,000 years ago. Hafted weapons show up sporadically, then disappear, then reappear later in more sophisticated forms. It's more like a slow burn, individual innovations flickering into existence, sometimes catching and spreading, sometimes dying out and needing to be reinvented later. The fire of behavioral modernity was smouldering for tens of thousands of years before it finally caught and spread across all human populations. But that makes it even more remarkable in a way. This wasn't genetic programming suddenly switching on. This was cultural evolution, messy, gradual, involving countless individual innovations that mostly failed but occasionally succeeded spectacularly. It was thousands of anonymous humans trying new things, teaching their children, sharing ideas with neighboring groups, slowly building the cultural infrastructure that would eventually transform their species. By 60,000 years ago, when the first modern humans finally left Africa, they weren't just anatomically modern. They were behaviorally modern too. They had symbolic thinking, sophisticated technology, complex social networks, and the cognitive tools to innovate rapidly when faced with new challenges. They were ready to encounter new environments, new resources, and new species. They were ready to become something unprecedented. Not just another successful species, but the species that would eventually dominate every ecosystem on Earth. But that was still in the future. For now, around 100,000 years ago, they were just beginning to explore what their enhanced cognitive abilities made possible. They were making art, wearing jewelry, hunting with sophisticated weapons, and trading with distant groups. They were becoming recognizably us, and the world would never be the same. Now here's where things get really interesting. You've got these three human species spreading across the world, developing technologies, creating culture, adapting to every environment from frozen tundra to tropical rainforests. But there's something else happening, something you can't see in the archaeological record, something that doesn't fossilize but might be the single most important evolutionary development in human history. They were learning to talk, really talk, not the simple warning calls that other primates use, not just pointing and grunting, full complex language with grammar, tense, conditional statements, the ability to describe things that aren't physically present, the power to say, 3 days ago I saw mammoths by the river where we camped last summer, and if we gather enough hunters we could go back there next week. That sentence, simple as it seems, requires cognitive abilities that no other species on Earth possesses. You need memory of past events, you need spatial reasoning, you need the concept of future planning, you need numbers, you need conditional logic, and you need the grammatical structure to string it all together in a way that another person can understand and act upon. When did this happen? Nobody knows for certain. Language is behavior, not bone, and behavior doesn't leave fossils. But geneticists have found some tantalizing clues. The most famous is a gene called FOXP2, sometimes sensationally called the language gene, though that's a massive oversimplification. FOXP2 regulates other genes involved in brain development, particularly in regions controlling fine motor movements of the face and mouth. Mutations in FOXP2 cause severe speech and language disorders in modern humans. You can think, but you can't translate those thoughts into coordinated speech sounds. The modern human version of FOXP2 is different from the version found in chimpanzees and other primates. Two specific mutations that appeared sometime in our evolutionary history, possibly between 200,000 and 400,000 years ago. But here's where it gets wild. When scientists finally sequenced the Neanderthal genome, they found Neanderthals had the exact same FOXP2 mutations we do, the same ones, which means those changes happened before the split between modern humans and Neanderthals, back during or right after that genetic bottleneck around 800,000 years ago. Neanderthals could speak. They had the genetic architecture for it. And if Neanderthals could speak, the Denisovans probably could too. All three post-bottleneck human species were developing language at roughly the same time, in parallel, because the selection pressures were identical. Small populations scattered across vast territories, dangerous environments where a single mistake could be fatal, complex technologies that required years of training to master, social networks that needed maintenance across generations. Under these conditions, any improvement in communication ability provided enormous survival advantages. But FOXP2 is just one piece of the puzzle. Language requires coordinated development of dozens of brain regions. The Broca's area for speech production, Wernicke's area for language comprehension, the ocuate fasciculus connecting them, enhance working memory to hold sentence structures in mind while processing them, the ability to create and recognize recursive patterns, sentences within sentences, thoughts within thoughts. All of this had to evolve together, a Rube Goldberg machine of neural architecture that, once assembled, gave humans something unprecedented. The ability to download the contents of one mind into another mind. That's what language really is. It's telepathy, just slower and less reliable than the science fiction version. You can take an experience you had, convert it into a string of sounds, send those sounds through the air, and someone else's brain can reconstruct an approximation of your original experience in their own mind. They didn't have to be there. They didn't have to see it themselves. You can give them your knowledge, your skills, your warnings, your discoveries, just by making specific mouth noises. This changed everything. Before language, human knowledge was trapped in individual brains. You could watch someone napping a stone tool and try to copy them, but subtle techniques, the angle of strike, the right amount of force, you had to figure that out through trial and error. Each generation had to relearn everything the hard way. With language, you could teach. Hold the hammerstone this way, strike at this angle. If the flake is too thick, you hit too hard. Complex skills could be transmitted verbally, broken down into steps, explained, corrected. The learning curve collapsed. What might have taken years of practice could be taught in weeks. More importantly, knowledge became cumulative. One person discovers fire hardening makes spear points more durable. They teach their children. One of those children figures out that certain woods work better than others. They teach their children. One of those children realizes you can shape the point before hardening it. They teach their children. Generation after generation, the knowledge builds. Each generation doesn't start from zero. They start from where their parents left off, then add their own innovations. This is called cumulative culture, and it's the secret to human dominance. No other species does this at our scale. Some animals have simple cultural traditions, nut-cracking techniques in chimpanzees, whale songs, but nothing approaches the complexity and persistence of human cultural evolution. And language is what makes it possible. But there's more. Language doesn't just transmit practical knowledge, it creates shared reality. When you name something, you make it real in a way that transcends individual perception. Before language, each human experienced the world alone, trapped in their own sensory bubble. With language you can say, "that bright thing in the sky," and point at the sun, and suddenly we both know we're thinking about the same object. We've created a shared symbol that exists between us. This power of naming, this ability to create shared symbols, was probably the foundation of human group identity. A clan could have names for their territory, their ancestors, their enemies. They could tell stories that explained who they were and where they came from. We are the people of the Red Rocks. Our ancestors came from the valley to the south when the great drought drove them away. The people beyond the western hills are our friends. The people from the northern forests are dangerous. These stories, these shared narratives, created cohesion stronger than anything kinship alone could provide. Groups could maintain identity across generations, even as individual members died and were replaced. The group became something larger than the sum of its parts, an entity with memory, tradition, continuity. And then there's planning. With language, you can discuss the future. Not just let's hunt tomorrow, but the herds usually migrate through the eastern valley during the new moon. If we send scouts ahead, we can position hunters at the narrow pass. We'll need at least 20 people, which means asking the river clan for help, which means we'll need to offer them part of the meat. This kind of collaborative planning, coordinating the actions of multiple groups across time and space, requires linguistic communication. You need to propose hypothetical scenarios, debate alternatives, come to consensus. All of this is impossible without complex language. Some researchers argue language didn't develop suddenly. They point out that the anatomical changes needed for speech, the descended larynx, the elaborate tongue muscles, took hundreds of thousands of years to evolve. They suggest language emerged gradually, becoming more complex as the neural and physical architecture slowly came together. Maybe early humans had simple proto-languages, strings of words without grammar, useful for basic communication, but lacking the recursive complexity of modern speech. Over hundreds of generations, as brain size increased and neural connectivity improved, language became more sophisticated. Grammar emerged, tense developed, abstract concepts became expressible. This gradual model makes sense from an evolutionary perspective. Complex traits don't appear overnight. They build slowly, each small improvement providing incremental advantages until eventually you have something unprecedented. But there's another possibility. Maybe the hardware for language, the genes like FOXP2, the brain architecture, the physical vocal apparatus, maybe all that evolved slowly over hundreds of thousands of years. But language itself, the actual use of these capabilities for complex communication, maybe that emerged much more suddenly. Think of it like this. A computer can have all the necessary hardware for running sophisticated software, but until someone writes and installs that software, the potential remains unrealized. Maybe human brains had the capacity for complex language for a long time before anyone figured out how to actually do it. Then one population, maybe during the genetic bottleneck when selection pressures were most intense, made the breakthrough. They figured out how to string words together grammatically. They developed syntax, recursion, all the cognitive tools that make complex communication possible. And once they had it, the advantage was so enormous that it spread rapidly through natural selection. Groups with sophisticated language outcompeted groups with simpler communication, not through violence necessarily, but through superior coordination, better knowledge transmission, more effective planning. Either way, gradual or sudden, by the time our ancestors left Africa 60,000 years ago, they had it. Full complex language, the ability to teach, to plan, to tell stories, to create shared reality through words, and maybe, just maybe, those first truly complex conversations happened around campfires. Picture it, night falling over the African savannah. A group of 30 humans, survivors of the bottleneck, gathered around flames that push back the darkness. Children sitting close to their parents, elders positioned where they can see everyone. The day's work finished, everyone fed, finally time to rest. And someone starts talking. Not about tomorrow's hunt or yesterday's danger, a story. When our ancestors first came to this valley, the voice rises and falls, painting pictures with words. Others listen, imagining scenes they never witnessed, learning history they never lived. Someone asks a question. Someone else adds a detail they heard from their grandmother. The story grows, becomes richer, more elaborate. This is the moment language becomes more than a tool. It becomes art, entertainment, the foundation of literature, poetry, myth, everything that makes us human rather than just smart apes. Those first campfire stories are lost forever. No recording exists, no written version survived, but their descendants endure. Every story ever told, every poem ever written, every song ever sung, they all trace back to that first human who realized words could do more than just convey information. They could move people, inspire them, bind them together in shared meaning. That was the real revolution. Not just talking, but storytelling. And once we started telling stories, we became something the world had never seen before. We became human. Now imagine this. You're standing on the African coast around 120,000 years ago. Behind you, stretching inland as far as you can see, is desert. Not the romantic, shifting sand dune desert of travel documentaries. Actual dead land. Cracked earth, withered vegetation, dust storms that can strip the skin from your bones, and it's been this way for longer than anyone can remember, longer than anyone's grandparents can remember, longer than the oldest stories passed down through generations. But in front of you there's the ocean, and the ocean means life. This is the world that forged modern human intelligence. Not stability, not abundance, chaos. The late Pleistocene epoch, roughly 130,000 to 11,000 years ago, was a period of climate instability so extreme it makes our current worries about climate change look quaint by comparison. We're talking about temperature swings of 10, sometimes 15 degrees Celsius happening over the course of just a few decades. Entire ecosystems transforming within a single human lifetime. Regions that had been lush grassland turning to desert in less time than it takes a child to grow up. These weren't gradual changes that populations could adapt to slowly over thousands of generations. These were catastrophic shifts that required immediate creative responses or extinction, and they happened over and over again. Ice ages advancing and retreating like enormous tides. Monsoon patterns shifting, causing mega-droughts that lasted not years but centuries. Sea levels rising and falling by hundreds of feet as glaciers grew and melted. Your ancestors didn't just survive this chaos, they were shaped by it, hammered on the anvil of environmental catastrophe until only the smartest, most adaptable, most innovative survived. The African mega-droughts were particularly brutal. Paleoclimate records from lake sediments and ocean cores tell us there were multiple periods when rainfall across most of Africa dropped to a fraction of current levels. Rivers dried up, lakes evaporated. The vast grasslands that had supported enormous herds of game animals turned to scrubland, then to desert. Population genetics suggests humans went through repeated bottlenecks during these events. Not the one massive bottleneck we discussed earlier, but multiple smaller crises that kept populations tiny and scattered. Groups that had numbered in the thousands suddenly crashed to dozens. Entire regions that had been inhabited for millennia were abandoned. But here's what's fascinating. These bottlenecks weren't random evolutionary setbacks. They were selection events, crucibles that tested every aspect of human capability. when resources collapsed and territories became uninhabitable, which humans survived? Not the strongest necessarily, not the fastest. The ones who survived were the ones who could think their way out of disaster, the ones who could innovate, who could look at a landscape that was killing them and figure out something new to eat, some new place to shelter, some new technique to extract water, or preserve food or protect vulnerable children. Every time a drought hit, it was like evolution running a brutal exam, and only the clever ones passed. This created an environment where intelligence was under constant selection pressure, not just general smarts, but specific cognitive abilities, pattern recognition to predict where resources might still be found, abstract thinking to develop new solutions to novel problems, social intelligence to maintain cooperation when everything was falling apart, memory to retain knowledge of distant water sources or seasonal resources that might not be available again for years. And the archaeological evidence shows this selection at work. During periods of maximum climate stress, we see innovation accelerating, new tool technologies appearing, evidence of more diverse diets, suggesting humans were learning to exploit resources their ancestors had ignored, signs of long-distance trade, implying complex social networks that could move information and materials across vast distances. The chaos was teaching them to be human. Now, where did people go when the interior became unlivable? The coasts. Coastal regions became refugia, havens where small populations could cling to existence while the inland territories turned hostile. The ocean doesn't care about droughts. It doesn't matter if the monsoons fail when you're sitting next to the largest source of protein on the planet. Genetic and archaeological evidence increasingly points to coastal populations as the survivors of the worst climate crises. When you look at the locations where human populations maintain themselves during maximum stress periods, they cluster around coastlines. South Africa, the Horn of Africa, possibly the Red Sea coast, places where the ocean provided a buffer against the catastrophes happening inland. And coastal living did something remarkable to human brains, literally. The shellfish and seafood theory of human brain evolution has been gaining traction among paleoanthropologists for the last few decades. Here's the basic idea. Brain tissue is metabolically expensive. It requires specific nutrients to develop properly, particularly omega-3 fatty acids like DHA. These fatty acids are relatively rare in most terrestrial diets, but they're abundant in seafood. Shellfish, fish, seaweeds, all packed with the exact nutrients developing human brains needed. Populations that shifted to coastal diets during climate crises weren't just surviving. They were consuming nutrition that literally allowed them to grow larger, more complex brains. Their children were being born with better neural development. Their cognitive abilities were being enhanced by their diet. Archaeological sites from this period show enormous middens, garbage dumps essentially, filled with shellfish remains. Not just the occasional treat, but systematic exploitation of marine resources. These weren't people who occasionally ate seafood. These were populations whose entire survival strategy revolved around the ocean. And there's something haunting about imagining those Ice Age coastlines. They didn't look like our coast today. Sea levels were sometimes 400 feet lower than they are now. What we think of as continental shelves, underwater today, were dry land. Vast coastal plains stretched for miles beyond the current shoreline. Your ancestors would have walked across landscapes that are now drowned, hunting on plains that are now fishing grounds. They would have watched the sea levels rise and fall over generations, coastlines advancing and retreating in response to ice sheets growing and melting thousands of miles away. The landscapes were alien, beautiful in ways we can barely imagine. During glacial maxima, the sky would have been clearer than anything we see today. Less moisture in the atmosphere meant stunning visibility. Stars so bright they cast shadows. the Milky Way like a river of light overhead. Cold, yes, but crystalline. Perfect. During interglacial periods, when things warmed up, the coast would have been lush, estuaries teeming with fish, mangrove forests, birds in such numbers they darkened the sky during migrations, a temporary paradise before the next climate swing. But beyond the simple survival advantages of coastal living, something more subtle was happening. Population dynamics during these climate oscillations created the perfect conditions for both genetic and cultural evolution. Think of it this way. During harsh periods, populations fragmented, small groups isolated in scattered refugia, separated by uninhabitable territories. They couldn't maintain contact. They developed independently, evolving slightly different genetic variants, developing slightly different cultural traditions. Then the climate would improve. Rains would return, grasslands would recover, and suddenly those isolated populations would expand, meeting each other again after thousands of years of separation. They would exchange genes, yes, through interbreeding, but more importantly, they would exchange ideas. This pattern of isolation and reconnection is exactly what drives rapid evolution, both genetic and cultural. During isolation periods, innovation is local, each group solving problems in their own way. Then during reconnection periods, the best solutions spread rapidly through the entire population. It's like natural selection working on culture instead of just genes. Groups develop different technologies, different survival strategies. When they meet again, the most effective innovations get copied and spread. The less effective ones are abandoned. Over and over, climate chaos splitting populations apart, then bringing them back together, each cycle refining human capabilities a little more. And the genetic evidence supports this model. Modern human DNA shows patterns consistent with repeated population bottlenecks, followed by expansions, periods of reduced diversity followed by periods of mixing, the signature of populations contracting into refugia during harsh periods, then expanding and interbreeding during recovery periods. We are the product of this chaos. Every rapid climate swing, every mega drought, every population bottleneck and recovery was an opportunity for selection to act. The humans who couldn't adapt died. The humans who could innovate survived and passed on their genes and their knowledge. This is why human evolution accelerated so dramatically during the late Pleistocene. It wasn't one thing. It wasn't a single mutation or a single environmental pressure. It was climate chaos creating an environment where innovation was literally a matter of life and death, where intelligence was under constant selection pressure, where populations were being split apart and recombined in ways that maximize both genetic and cultural evolution. The Ice Ages didn't just happen around our ancestors. They happened to them, through them, forging modern human cognition in the crucible of environmental catastrophe. And when the climate finally stabilized around 11,000 years ago, we weren't the same species that had entered the chaos 100,000 years before. We were something new, something unprecedented. Humans with brains capable of symbolic thought, abstract reasoning, complex language, and technological innovation. We were ready for what came next. We just didn't know it yet. But survival wasn't just about better tools or warmer clothes or knowing which plants wouldn't kill you. The real secret, the thing that would eventually separate humans from every other species on the planet, was happening inside our social structures. Because around 100,000 years ago, something remarkable was occurring. We were learning to think together. Picture a typical human group 200,000 years ago. Maybe 15, 20 people, extended family mostly. A few children, some adults in their prime, maybe one or two elders if they were lucky. Everyone knew everyone else intimately. You didn't need sophisticated social skills to navigate relationships when you'd known the same 12 people your entire life. Your brain could handle that easily. But by 100,000 years ago, something had changed. Groups were getting bigger, not massively bigger, but significantly larger. Archaeological evidence from this period shows larger dwelling sites, more diverse tool assemblages, signs of more people living and working together, and this created a problem that would require an evolutionary solution. A British anthropologist named Robin Dunbar figured out something fascinating about primate brains. There's a direct correlation between the size of a primate's neocortex and the size of its social group. The bigger the brain region responsible for social cognition, the more individuals that primate can maintain stable relationships with. For most primates, that number maxes out around 50. Chimps can manage groups of about 50 individuals before social cohesion breaks down and the group fractures. But humans can maintain stable social relationships with around 150 people. We call it Dunbar's number. This isn't just about recognizing faces. It's about tracking complex social information. Who's related to whom? Who owes favors to whom? Who can be trusted and who's a troublemaker? Who's good at hunting versus who's good at healing? It's an enormous amount of data to process, and it requires serious computational power. The kind of computational power that only a very large, very sophisticated brain can handle. Around 100,000 years ago, human groups were pushing past the limits that had constrained our ancestors for millions of years. Instead of bands of 20 or 30, we were forming communities of 50, 80, maybe 100 individuals, not living together constantly necessarily, but maintaining regular contact, recognizing each other as part of the same social network. And this expansion didn't just happen randomly. It happened because larger groups provided massive survival advantages. More hunters meant more reliable food acquisition. More gatherers meant better knowledge of plant resources. More toolmakers meant better equipment for everyone. More warriors meant better defense against predators and rival groups. But maintaining cooperation among 100 individuals is exponentially harder than maintaining it among 20. With 20 people, everyone can monitor everyone else's behavior directly. Cheaters and freeloaders get caught immediately. Social pressure keeps everyone in line. With 100 people, you can't watch everyone all the time. You need rules, social norms, reputation systems. You need to be able to remember that the guy from the group 3 valleys over is trustworthy, even though you haven't seen him in 6 months. You need to track alliance networks, understand hierarchies, navigate complex webs of kinship and obligation. This required a cognitive revolution. Our brains had to develop new capacities for social reasoning, new mechanisms for tracking relationships, new emotional responses to maintain group cohesion. We became gossips. And that might sound trivial, but it's not. Gossip is how humans enforce social norms in large groups. It's how information about cooperation and defection spreads through networks. It's how reputations get built and destroyed. Anthropologists have found that about 2/3 of human conversation is social gossip. Who did what with whom? Who can be trusted? Who violated group norms? This isn't just entertainment. It's the operating system that makes large-scale human cooperation possible. But the expansion of social networks did something else, something even more profound. It created what archaeologists call the ratchet effect. When you live in a small, isolated group of 20 people, knowledge is fragile. The guy who knows how to make the best spear points, if he dies in a hunting accident before teaching anyone else, that knowledge dies with him. The group has to reinvent it from scratch, if they ever do. Loss of knowledge is a constant threat. Every generation risks forgetting what the previous generation knew. But when you're part of a network of 100 people, connected to other networks through trade and kinship ties, knowledge becomes durable. The guy who makes the best spear points teaches 5 apprentices. They teach others. The technique spreads across multiple groups. Even if disaster strikes one community, the knowledge survives in others. And here's the magic part. Knowledge doesn't just survive, it accumulates. Someone figures out a better way to have the point to the shaft. Someone else discovers a superior stone for the blade. Someone else invents a technique for making the point sharper. Each innovation builds on previous innovations. Nothing is lost, everything is gained. The ratchet only turns one way, forward. This is what made human cultural evolution so radically different from genetic evolution. Genetic evolution is slow, operating over thousands of generations. Cultural evolution can be explosively fast, operating over a single lifetime. A child can learn in months what took their ancestors thousands of years to discover, and then that child can add their own innovations on top. By 100,000 years ago, this ratchet effect was accelerating. Trade networks were expanding, connecting groups that had never been in contact before. And trade wasn't just about exchanging goods, it was about exchanging ideas. Imagine a coastal group that's developed sophisticated fishing techniques meeting an inland group that's mastered fire-starting methods. They trade fish for fire-starting tools, but they also trade knowledge. Within a generation, the coastal group has better fire management. The inland group has started fishing in rivers. Both groups are now more successful than either was before. Nobody invented anything new. They just shared what they already knew. But the effect on survival, massive. Archaeological sites from this period show exotic materials appearing hundreds of miles from their sources, seashells in landlocked regions, stone tool materials traded across vast distances. This isn't just stuff moving around. It's people meeting, communicating, sharing knowledge, teaching each other survival strategies that had been developed in completely different environments. Every trade meeting was a conference, every exchange an opportunity for innovation to spread. And then there's the grandmother effect. Most mammals don't live long past their reproductive years. Once you can't reproduce, evolution doesn't care what happens to you. But humans are different. Human females undergo menopause, ceasing reproduction decades before they die. This seems wasteful from an evolutionary perspective. Why would natural selection allow it? The answer is that grandmothers are incredibly valuable, not for making babies, but for teaching. A woman in her 50s or 60s who has survived droughts, famines, climate shifts, she carries knowledge that younger adults haven't accumulated yet. She knows which plants stay edible when everything else fails. She remembers the location of water sources that only flow during certain seasons. She's seen children through diseases that younger mothers might panic about. She's a walking library of survival information. In small, isolated groups, this knowledge would help, but its impact would be limited. In large, interconnected networks, it's transformative. Grandmothers become teachers, advisors, repositories of cultural knowledge that can be transmitted across multiple generations. The archaeological record suggests human lifespans were increasing during this period. More people were surviving into their 50s, 60s, even 70s. Not because life was easier, it probably wasn't, but because groups that supported their elders, that valued accumulated knowledge over just physical strength, those groups survived better. Population density was increasing too, slowly, unevenly, but increasing. And denser populations meant more interactions, more exchanges, more opportunities for innovation to spark and spread. There's a direct correlation in the archaeological record. As sites show evidence of larger populations, they also show evidence of more cultural complexity, more tool types, more art, more evidence of symbolic behavior. It's not that denser populations were smarter individually. It's that they were smarter collectively. More brains working on problems, more perspectives to draw from, more chances for someone to make a connection nobody else had seen. Think about what this would have felt like on the ground. For millions of years, your ancestors had lived in small bands, seeing the same faces every day, rarely encountering strangers. But now, maybe once a year, several groups would meet at some neutral location. a water source that never dried up, a natural shelter, a place where seasonal migrations of prey animals created hunting opportunities. 50 people from different groups, maybe 100 if it was a particularly good year. The young ones staring at each other with curiosity and nervousness, the elders negotiating alliances, arranging marriages between groups to strengthen kinship ties, the skilled craftspeople comparing techniques, admiring each other's work, maybe trading tools or teaching each other their methods. These gatherings would have felt momentous, a festival, a celebration, but also deadly serious. These were the occasions when knowledge transferred, when innovations spread, when social bonds got forged that would hold the larger network together through the harsh seasons. There would be storytelling around fires, stories about ancestors and great hunts and dangers survived, stories that encoded practical survival information in memorable narratives. There would be displays of skill, competitions maybe, ways of establishing reputation and status. There would be conflicts too, disputes to resolve, grievances to air, social tensions to navigate, all requiring sophisticated communication, emotional intelligence, the ability to understand and predict others' behavior. Your brain was evolving to handle all of this. Generation by generation, natural selection was favoring individuals who excelled at social cognition, the ones who could read subtle emotional cues, the ones who could remember complex relationship networks, the ones who could navigate social hierarchies without causing offense, the ones who could build alliances and maintain them over years despite rarely seeing their allies. These individuals left more descendants, passed on more of their genes, shaped the trajectory of human evolution. We weren't just getting smarter about hunting or tool-making, we were getting smarter about each other, and that intelligence, that sophisticated social cognition, that was the foundation everything else would build on. Because once humans could cooperate reliably in groups of dozens, eventually hundreds, eventually thousands, there was essentially no limit to what we could accomplish. We could pull knowledge across generations, share innovations across vast distances, tackle problems too complex for any individual mind. We could think collectively, and collective thinking would prove to be the most powerful force in human evolution. The social brain revolution was accelerating, and it was about to enable innovations that would have seemed impossible just a few thousand years before. Imagine pressing pause on the world 120,000 years ago. Humans are already clever, already social, already carrying the scars and strengths of the great bottleneck. They're making tools, building alliances, telling at least simple stories around the fire. Now press fast forward. In what feels like an instant on the evolutionary clock, something shifts. Art explodes. Tools become finely crafted, specialized, almost engineered. Long-distance trade networks lace together continents. Myth, ritual, and complex language bloom. So what happened inside our cells while all this was happening outside? Geneticists have a phrase for the places in our DNA that look like they suddenly started evolving much faster than expected. They call them human accelerated regions, HARS. Most of our genome plods along at a slow, steady pace, changing bit by bit over millions of years. But here and there you find stretches of DNA where evolution seems to have slammed the gas pedal. When scientists compare our genome to that of chimpanzees, gorillas, or even Neanderthals, these human accelerated regions light up like tiny flares. Places where, for reasons we still don't fully understand, natural selection seems to have gone to work in overdrive. Many of these regions are near genes related to brain development, synapses, and how neurons talk to each other. They're not usually the famous big genes that directly build brain tissue. They're more like little switches, dials, and regulators. They turn genes on and off at just the right time, in just the right cells, during development. Change those switches, and you don't just get a slightly bigger brain. You might get a brain wired a bit differently, more flexible, more plastic. better at forming complex networks of ideas, memories, and social relationships. One of the most intriguing HARs is called HAR1. In chimps and other apes, it looks almost unchanged over tens of millions of years. In humans, in just a few million years, it has transformed. HR1 is active in developing brain tissue during early fetal growth, especially in a layer of cells that helps organize the cerebral cortex, the wrinkled outer layer of the brain where planning, language, and abstract thought live. Did a few mutations in HAR1 gently nudge our brains toward deeper complexity? We don't know. But the timing is suggestive. These accelerated regions often sit right at the crossroads of brain structure and function, like quiet engineers behind the scenes, rewriting the wiring diagram. And then there are the headline genes, the ones that tend to grab popular attention because they have names and stories attached to them. Two of the most famous are MCPH1 and ASPM. Both are involved in regulating brain size during development. When they break in extreme ways, you can get microcephaly, brains that are much smaller than average, with serious impacts on cognition. That makes them obvious candidates for the question, what changed in our DNA to give us larger, more complex brains? When researchers looked at the evolutionary history of MCPH1, they found signs of recent positive selection in humans. The gene seems to have gone through a rapid series of changes not that long ago in evolutionary terms. ASPM shows a similar story. Signs that certain versions spread quickly through human populations, as if they offered some advantage. Some scientists propose that new variants of MCPH1 and ASPM might have swept across humanity in the past 100,000 years, perhaps boosting brain function or fine-tuning areas involved in language or social reasoning. Other studies suggested that these genes might have influenced how quickly brain cells divide, subtly shaping brain growth patterns in infancy and childhood. It's a tempting narrative. A couple of key mutations, a few coding changes, and suddenly we're composing music, carving figurines, building symbolic worlds. But as genomic data improved, the story got more complicated. Those signs of recent selection turned out to be messy. Some signals weren't as strong as early studies suggested. Other analyses found that changes in MCPH1 and ASPM may have happened earlier than the so-called Great Leap Forward, or that their impact might not be as dramatic as once hoped. The genes are still important. They clearly help shape our brains. But they might be more like part of a chorus than lone soloists. And this leads to one of the deepest questions in human evolution. Did genetic changes come first, creating brains capable of modern behavior? Or did behavior change first, with culture pulling our genes along behind it? It's the brains before culture versus culture before brains puzzle. One possibility is that, by 200,000 years ago, our ancestors already had brains virtually as capable as ours in raw hardware terms. The size, the folds, the basic wiring plan were already in place. But they weren't yet using that hardware to its full potential. Social structures, population density, and communication systems were still too simple to demand the full power those brains could offer. In that view, the genetic groundwork was laid early, and the explosion of symbolic culture around 100,000 years ago was more like switching on a machine that had been sitting idle. Another possibility, key genetic tweaks to brain development, neural plasticity, or language circuits happened closer to the time of the behavioral shift. A gradual accumulation of small changes in many genes crossed a threshold. Suddenly the same size brain became more efficient at linking ideas, imagining alternatives, or learning from others. Culture then snowballed on top of those fresh genetic foundations. The uncomfortable truth is that we don't know which came first, brain, culture, or a subtle duet between the two. And there's another layer, one that blurs the line between genes and environment, epigenetics. Your DNA sequence is like a script. but your cells can mark that script with little chemical notes, highlighting some lines, crossing out others, and changing which scenes get performed. These changes don't alter the underlying letters of your genes, but they can powerfully affect how much of a gene gets used and when. Stress, diet, disease, social environment, and even patterns of parenting can all influence these epigenetic marks. Some of them can be passed down across a few generations, like ghostly echoes of past environments for children and grandchildren. Now think back to the bottleneck. 117,000 years of grinding hardship, starvation, extreme weather, constant danger. Then the slow shift into a world that was still unstable, but full of new opportunity. What if those radical environmental changes didn't just select genes, but also rewired how those genes were expressed? It's possible that many of the genetic variants that make our brains so flexible were already present long before the Great Leap Forward, quietly carried in small pockets of early humans. But under the crushing stress of the bottleneck and the inventive problem-solving it demanded, epigenetic systems may have shifted. Brains might have grown more responsive to learning, more sensitive to social input, more tuned to language-like patterns. When the climate eased and populations grew, those epigenetically primed brains would suddenly be operating in a richer social and cultural environment. That, in turn, might feed back into the genome itself, because individuals whose gene expression patterns worked best in this new, complex world would leave more descendants. Over many generations, genes and epigenetic tendencies could lock in a feedback loop, sculpting minds that were not just big, but incredibly adaptable. Then there's the part of the story that feels almost like science fiction. We weren't evolving alone. When our ancestors wandered out of Africa and into the territories of Neanderthals and Denisovans, they didn't just compete with them, they mated with them. Every person with non-African ancestry alive today carries Neanderthal DNA, usually about 1 to 2%. Many people in Asia and Oceania carry small but significant amounts of Denisovan DNA as well. These aren't just random leftovers. Some of the borrowed genes appear to have been incredibly useful. Neanderthal DNA has been linked to immune system genes, skin structure, and how our bodies react to cold climates and ultraviolet light. Denisovan DNA has been tied to altitude adaptation in Tibetans, helping their blood handle low oxygen on the high plateau. Other segments may have influenced how we process fats, respond to certain pathogens, or even how our brains develop. It's as if, when modern humans moved into new environments, they sometimes bypassed the slow grind of waiting for new mutations to arise. Instead, they tapped into genetic solutions already explored by their cousins. Hybrid children who inherited the right mix of genes might have done especially well on icy plains, in dense forests, or on windswept mountainsides. Did any of these introgressed genes nudge our cognition in subtle ways? Possibly. Some Neanderthal segments sit near genes involved in brain development and neurochemistry. The evidence is fragmentary, and the effects, if they exist, are likely modest. But it raises an eerie thought. The way you think, the way you sleep, perhaps even the way your mind wanders as you drift off, might carry faint influences from minds that no longer exist. All of this genetic complexity, HARs, brain genes, epigenetics, introgression, sounds dramatic. It's easy to fall into a kind of gene worship, imagining a single mutation that created art, or speech, or morality. And that brings us to the controversy. Some researchers worry that the genetic story is overshadowing something equally, if not more, important: culture. Brains don't invent symbolic art in isolation. They do it in groups, around hearths, during shared hunts, in rituals that bind communities together. You can have all the right genes for language, but if you grow up alone without exposure to speech, you never acquire it fully. You can have a brain primed for complex social understanding, but if you live in a tiny group with little innovation, your cultural world will remain simple. As populations grew after the bottleneck, as networks expanded and knowledge began to accumulate, culture started to act like a second form of inheritance. Ideas were passed down and refined generation after generation. Technologies didn't have to be reinvented from scratch. They could be built upon. In this view, the sudden acceleration of human behavior around 100,000 years ago might not signal a genetic revolution at all. It could reflect a cultural tipping point. Enough people, in enough connected groups with enough time, finally created a self-sustaining engine of innovation. Genes made that possible, but they didn't script the whole play. And yet, even when we try to defend culture from genetic reductionism, we keep circling back to those other humans, the ones who also had big brains, complex societies, and sophisticated tools, but whose lineage is ended. Neanderthals, Denisovans, not distant aliens, but close cousins. Intimate enough that, when we met them, we started families with them. Close enough that bits of their DNA are still whispering in our cells. It's hard not to wonder what their minds were like. Did Neanderthals watch the same stars and give them names in languages we'll never hear? Did Denisovan parents tell bedtime stories on islands now lost beneath the sea? Did they have their own accelerated regions, their own quiet genetic sparks that almost, but not quite, led to a different history? When we search our genome for the secrets of the last 100,000 years, we're not just decoding ourselves, we're glimpsing the shadows of those vanished relatives. The places where our DNA diverged from theirs may hold clues about why we painted caves and composed songs, while their traditions ended in silence. But the differences are small, tiny tweaks in gene regulation, slight shifts in brain development, maybe nuances in how dopamine or serotonin shaped motivation and curiosity. Not a gulf, just a narrow, winding river. On one side, our ancestors. On the other, relatives who became part of us, but also disappeared as distinct peoples. In that narrow river, somewhere between genes and culture, between biology and history, lies the mystery of why human evolution suddenly accelerated. The next step in the story is not just about what we were born with, but what we did with it. How minds forged in ice ages and bottlenecks began to dream in colour, carve meaning into bone and stone, and turn the raw material of thought into art and ritual. And that is where we go next. By the time your ancestors were walking out of Africa and brushing shoulders with Neanderthals and Denisovans, something even stranger than stone tools and trade networks had begun to appear. Marks. Not just the accidental scratches of everyday life, but deliberate, repeated, patterned marks. On pieces of ochre, on bone, on cave walls. Lines that didn't cut meat, scrape hides, or shape spear points. Lines that didn't do anything, except mean something. Somewhere between 100,000 and 40,000 years ago, scattered across Africa, Europe, and Asia, humans and our close cousins started doing something no other species had ever done at this scale. They began to create symbolic worlds. We can trace the first faint glimmers. A piece of red ochre from Blombos Cave in South Africa, about 75,000 years old, carved with a cross-hatched pattern. Not random, not a side effect. The lines are ordered, intentional, repeating. Whatever it meant something to the person who carved it. In the same cave, tiny beads made from seashells, perforated so they could be strung and worn. Decoration, identity, maybe status, maybe group membership. Whoever wore them was telling the world, I am this, not that. In North Africa and the Middle East, similar beads show up. The design's different, but the idea is the same. Small pieces of the natural world transformed into symbols that could be carried on the body. Later, in Europe, the figurines appear. the so-called Venus figures, tiny carved shapes with exaggerated hips and breasts smoothed by human hands. They don't look like accurate portraits. They look like ideas, fertility, womanhood, ancestors, goddesses, or something else entirely that we can't quite reconstruct. Then the cave walls come alive. In places like Chauvet, Lascaux and Altamira, deep underground, far from daylight, the rock explodes with images. Horses in motion, mammoths, bison, lions, abstract signs and dots, stencils of human hands pressed against the stone and outlined with sprayed pigment. None of this is strictly necessary for staying alive. You can hunt, cook, and raise children without ever drawing a bison at all. And yet, all across the world, in different times and different places, humans chose to do this. They chose to take time away from survival, to make symbols. What does that tell us about their minds? To carve a geometric pattern on ochre, or paint a running horse in flickering firelight, your brain has to do something profound. You have to separate appearance from meaning. You have to understand that this line, this shape, this colour, can stand for something that is not physically present. A person, an animal, a spirit, a memory, a rule. This is symbolic thinking. It's the same mental trick that lets a sound like tree stand for an actual tree, or a clan mark stand for a family, or a simple crosshatched design stand for an idea only your group understands. Symbolic thinking means your brain can build internal models of things that aren't right in front of you, then share those models with other people. It's not just more intelligence, it's a different kind of intelligence. You start getting layers of meaning, metaphors, stories. This mark is a bison. This bison is our prey. This prey is a gift from the spirits. These spirits watch over us when we sleep. Once you can do that, your mind is no longer trapped in the immediate present. You can move through time and possibility. You can remember the dead. You can imagine the unborn. You can picture worlds that no one has ever seen. The archaeological record suggests this shift didn't happen all at once. It looks more like a long, uneven dawn. A scratched line here, a bead there, a figurine carved during a long winter, a handprint in the back of a cave. But taken together, they reveal a change in cognitive architecture. A brain wired not just for problem solving, but for meaning-making. Not just for reacting to the world, but for inventing invisible worlds and living inside them. You can see this most clearly in how our ancestors treated their dead. Before this period, bodies are mostly just left. Maybe moved a little, maybe scavenged. Death is a physical event, a practical problem. Then, among Neanderthals and later among modern humans, we start to see something new. Bodies carefully placed in pits, sometimes curled on their sides, in positions that look like sleep, sometimes with tools, animal bones, flowers, pigments, ornaments. In Shanidar Cave in Iraq, a Neanderthal skeleton appears to have been laid to rest with clumps of pollen from flowering plants, as if someone had scattered blossoms over the grave. This interpretation is debated, but the possibility alone is striking. In later modern human sites, burials become even more elaborate. Red ochre sprinkled over bodies, turning them the colour of blood, of life. Shell beads arranged around the head and chest. Weapons and jewellery placed beside the dead as if they might still need them. These are not behaviours you see in animals simply reacting to a dead body. This is ritual. Ritual means you are treating death as something more than biological shutdown. You are framing it with meaning. Maybe you believe the person is going somewhere, or watching from somewhere, or becoming something else. Maybe you don't have a clear doctrine, just a powerful shared feeling that this transition matters. You don't develop rituals like that without symbolic thinking. You have to be able to conceive of an after, a continuation, a relationship with someone who's no longer physically present, The first graves are not just holes in the ground. They are the earliest architecture of the invisible. Around the same time, another kind of invisible structure is forming: music. We rarely find instruments from this period because wood and skin decay. But sometimes, in just the right conditions, something survives. A hollow bird bone pierced with carefully spaced holes. A fragment of mammoth ivory carved into a narrow tube. When these are reconstructed and played, they produce notes, scales, melodies. Bone flutes from Europe, 35,000 to 40,000 years old. Older possible instruments from other regions. They're not perfect records of the first music, but they're proof that by this time, your ancestors were doing more than banging rocks together. They were shaping sound. Music doesn't leave the same obvious traces as a stone spear. But think about what it tells us. To design a flute, you need to imagine notes before they exist. To play one, you need to coordinate breath, fingers, and timing. To play together with others, you need a shared sense of rhythm and pattern, and you probably needed all of that long before the first flute was carved. Humans are rhythmic animals, footsteps, heartbeats, the crackle of fire, the seasons. It seems overwhelmingly likely that long before someone drilled holes in bone, groups were clapping, drumming on logs, humming, chanting. Why? Rhythm synchronizes nervous systems. When you move or sing in unison, your brain activity literally starts to line up with the people around you. Oxytocin rises, boundaries soften. You feel with the group in a way that is hard to describe and hard to let go of. For a small band balancing on the edge of survival, that feeling is priceless. Music becomes invisible social glue, a way of telling each other, without words, I am with you, we move together, we will share the hunt, the hardship, the night. And if you already believe in spirits, ancestors, or forces you can't see, music becomes the language you use when ordinary speech feels too small. This is where art and ritual start to merge. Picture a group preparing to enter a cave to paint. Torches are lit. Pigments are ground. Maybe someone begins a low, steady drumbeat on a rock. Voices rise and fall, echoing off the stone. The air is thick with smoke and breath. They're not just decorating a wall. They're stepping into a different kind of space, which brings us to one of the strangest choices our ancestors ever made. They went into the dark. Many of the most spectacular cave paintings are not near the entrance. They're deep inside, through narrow passages, down slippery slopes, in chambers where you have to crawl to get in. Places where a dropped torch means total, crushing blackness. Why go there? They could have painted on cliff faces, on rock shelters open to the sky. Sometimes they did. But over and over, again and again, they chose to descend into the earth to do their most elaborate work. Some researchers think the cave itself was part of the meaning. In many traditional cultures, caves are portals, wombs of the earth, entrances to the underworld, places where gods, spirits, or ancestors dwell. If you already see the world as layered, this world, the spirit's world, the ancestors' world, then going underground is not just a practical choice, it's a journey. The flicker of fire on uneven rock, the booming echo of your voice in a chamber that feels alive, the way your torch makes painted animals appear to move. It's easy to imagine how that would feel like crossing a boundary. It's possible that some of the people who painted those caves were specialists in crossing boundaries, shamans in the broad sense. People who knew how to induce altered states of consciousness through drumming, dancing, chanting, fasting, exhaustion, or plant substances. Modern neuroscientists studying cave art have noticed something odd. Some of the abstract signs and patterns resemble the kinds of visual hallucinations people report in trance states. Zigzags, grids, spirals, radiating dots. When the brain is pushed away from its ordinary waking mode, through sensory deprivation, sleep deprivation, or certain chemicals, it tends to produce a predictable toolkit of shapes and visions. These may then be interpreted as spirits, animals, messages from beyond. If something like that was happening in Paleolithic caves, then the art on the walls might be more than decoration or storytelling. It might be a record of journeys taken with the mind. We will probably never know exactly what those artists thought they were doing, but the combination of deep darkness, echoing sound, firelight, and repeated imagery suggests more than idle doodling. It suggests ritualized encounters with the invisible. Now imagine yourself standing there, not as a scientist, not as a distant observer, but as a quiet visitor. You walk into a modern cave where ancient paintings still survive. The guide's flashlight clicks off. For a moment there is only the soft battery-powered glow on the walls. Horses leap across rock that looks like it's breathing. Red handprints bloom beside black outlines of bison. You're told that these hands belong to someone who lived 20,000, 30,000, maybe 40,000 years ago. A person with a life as detailed and complex as yours. Loves, fears, memories, inside jokes, nightmares, a favourite place to sit by the fire. They pressed their hand against the stone. Someone else blew pigment over it, filling the gaps, turning warm skin into cold mineral shape. Then they took their hand away. What's left is absence made visible, a sign that says silently, I was here, I reached out, I touched this world. Standing in front of that, you're doing something very old and very new at the same time. You're using the symbolic mind they helped create to understand the symbolic world they left behind. Art, ritual, music, burial, caves, altered states. These are not separate inventions. They're different branches growing from the same root. A brain that can imagine more than what's in front of it. A mind that refuses to accept that reality is only what can be touched and eaten. A species that insists on filling the darkness with meaning. Once that kind of mind exists, evolution takes on a new dimension. Ideas can shape behavior, beliefs can drive cooperation, stories can bind groups together or tear them apart. From this point on, human evolution is not just about bones and genes, it's about symbols. And those symbols are about to travel very, very far from the caves where they were first painted. Picture the shoreline at dusk, 70,000 years ago. The heat of the day is fading. The air smells of salt and wet stone. Waves slide in and out with the slow rhythm of a sleeping animal. On a narrow strip of African coast, a small band of humans is getting ready to move. They don't know they're about to change the world. To them, this is just another journey, another stretch of coastline to explore, another headland to round, another bay to search for shellfish, stranded fish, driftwood, and fresh water. But from our perspective, watching across tens of thousands of years, this is the beginning of something enormous. This is the Great Dispersal. The moment when a few hundred descendants of those bottleneck survivors stepped out of Africa for good, sometime between about 70,000 and 50,000 years ago, and began the journey that would take their children to every habitable continent on Earth. They weren't the first humans to leave Africa. Earlier humans, including Homo erectus and perhaps even earlier groups of our own species, had ventured into Eurasia long before. But they hadn't stayed dominant. Climate swings, competition, and time had erased most traces of those earlier expansions. This time was different. These were fully behaviorally modern humans, carrying with them the cognitive toolkit honed during that 117,000-year bottleneck. Complex language, flexible social networks, standardized tools, the ability to innovate under pressure and pass those innovations on. When they began moving out of Africa, they carried something new into the wider world. Not just genes, but culture, that could evolve faster than DNA. And the world they were about to enter would demand everything they had. Leaving Africa didn't mean crossing a clear line on a map. It meant following opportunities step by step, often without realizing how far you'd gone until turning back wasn't really an option. Along the Red Sea coast, then across into the Arabian Peninsula, the same pattern probably played out hundreds of times. A few families followed the shoreline, hunting, gathering shellfish, tracking the movements of animals. When the local resources thinned out or the climate shifted, they kept going. The coastal route theory suggests that many of these early migrants hugged shorelines rather than plunging inland. From the Arabian Peninsula along the southern coast of Asia, through what's now Iran, Pakistan, India, Southeast Asia, and eventually toward Australia, they moved in small jumps, always within reach of water and marine life. From a survival standpoint, it makes sense. Coasts offered predictable food sources: shellfish, seaweed, fish caught in tidal pools. You didn't need specialized big game hunting skills to survive. You needed sharp eyes, nimble hands, and a good memory for which coves were richest at which tides. But even a gentle path like this demanded constant adaptation. Every stretch of coastline was different. New shellfish species, new predators, new weather patterns, new diseases lurking in warm tidal flats. What worked on one beach might fail 2 headlands away. Innovation wasn't optional, it was routine. You can imagine the quiet experiments, a new way of cracking shells, a better way to carry water along dry stretches, a different kind of shelter built to withstand salt-laden winds. Someone tying a stone to a line of plant fibre, discovering a more effective way to catch fish. Someone else learning how to predict tides by the position of the moon. Most of these experiments failed and were forgotten, but the ones that worked spread, family to family, campfire to campfire, sometimes travelling faster than the people themselves. News of a rich bay or a dangerous reef might move ahead of the migrants, like a whisper running along the coast. Migration didn't just move people, it moved ideas. As groups moved farther from Africa, the environments they encountered became more and more varied. Tropical coasts gave way to monsoon-drenched river valleys. Humid forests bristled with unfamiliar plants and poisonous animals. Inland, savannas shifted to shrubland, then steppe, then cold, dry plains. Every new biome was like a different exam in survival, testing a different part of the human toolkit. In the tropics, the challenge was managing abundance. So many plants, so many animals, but which were edible, which were dangerous, which required processing or careful preparation. Trial and error here meant life and death. Over time, local knowledge deepened. Which roots to soak, which leaves to boil, which fruits to avoid. This favoured careful observation, detailed memory, and the ability to transmit subtle, context-heavy information to the next generation. Further north, the challenges shifted. Short growing seasons, long cold winters, herds of large animals moving in seasonal migrations. Here you needed planning, storage, clothing that could keep you alive when temperatures plummeted, shelters that could resist ice and wind. In these harsher climates, you start seeing clear signs of new technologies. Tailored clothing made from multiple animal hides, bone needles, more complex hearths, improved hunting weapons. People began coordinating large-scale hunts, driving herds into natural traps or toward ambush points, then processing enormous quantities of meat and fat to carry them through the lean months. Each environment demanded a different set of strategies, each demanded different mental skills, and because human culture could adapt much faster than genes, every new landscape acted like a catalyst, pushing groups toward new solutions. Migration didn't slow evolution down, it sped it up. But the land and climate weren't the only forces shaping these travellers. They weren't alone. Out of Africa, the world was already occupied by other humans, Neanderthals in Europe and parts of Western Asia, Denisovans farther east, and possibly other archaic groups we've barely begun to understand. For our expanding Homo sapiens populations, meeting them must have been one of the most intense experiences imaginable. Sometimes these meetings probably went badly. Competition over hunting grounds or water sources, conflicts fought with spears and stones, or simply with the slow pressure of one population pushing another into marginal habitat. But the genetic and archaeological evidence suggests something more complicated than simple replacement. We know there was interbreeding. Modern non-African humans carry Neanderthal DNA. Some populations in Asia and Oceania carry Denisovan DNA. These weren't one-time events. They seem to have happened multiple times over thousands of years. That means at least some encounters weren't fights. They were meetings, negotiations, exchanges, possibly even long-term alliances. Imagine that. Two bands see each other across a valley. The shapes are similar, but not quite the same. The faces are familiar enough to read expressions, but different enough to seem uncanny. Voices carry in the cold air, strange but patterned. There's tension, fear, curiosity. Over days or weeks, maybe they edge closer, trading gestures, objects, sounds. A piece of worked stone that shows a technique one group has never seen before. A plant that only one side knows is edible. A new way of binding wood and stone together. Eventually, perhaps, a few individuals move between groups as mates. In those moments, evolution is happening faster than any mutation could manage. Two entire cultural lineages meet, compare notes, and reorganize. Competition probably pushed innovation too. If a neighboring group hunted more effectively, you'd feel the pressure immediately. Fewer animals, scarcer resources. Suddenly, there was an incentive to improve your tools, refine your strategies, or move into new niches. Night hunting, fishing, plant gathering, anything that could reduce direct overlap. Cooperation could be just as powerful. Shared hunting drives, coordinated seasonal movements, exchanges of material and knowledge along what might have been early human trade routes, strung out across thousands of miles and dozens of generations. The world outside Africa became a laboratory where human species tested and cross-pollinated their best ideas. As some groups kept following the southern coastal route deeper into Asia, others began pushing inland or turning north. These inland migrations opened new chapters in the story. High plateaus with thin air, mountain ranges that forced detours or demanded new climbing and shelter skills, swamps pulsing with insects and disease, open steppes where wind seemed to blow forever, with no trees to break the horizon. Reaching these places wasn't just a matter of walking farther. It required mental leaps. You had to learn to read snow and ice, to predict avalanches, to find edible plants under frost-hardened ground. In mountains, you needed to understand altitude sickness long before anyone knew what oxygen was. In disease-ridden lowlands, you needed rules, clean water sources, ways of disposing of waste, perhaps early forms of herbal medicine, just to keep your group from collapsing. Far to the north, on the way to what would one day be Siberia and the Arctic Circle, the adaptations became extreme. Mammoth and reindeer hunting, permanent or semi-permanent dwellings built from bone, hide and turf, lamps burning animal fat to provide heat and light during long winter nights, clothing layered and sewn with precision. Here, failure of innovation meant freezing to death, yet humans kept going, across massive river systems, over land bridges exposed during Ice Age low sea levels. Some would eventually cross into the Americas, others would reach the far islands of the Pacific. Every successful crossing required ideas that had never existed before. New watercraft, new navigation strategies, new social norms to keep small groups cohesive during long, risky journeys. The people who made these moves weren't just survivors. They were explorers in a deep, almost instinctive sense. As bands spread out over thousands of miles, something else happened. Isolation. Groups that once shared common stories, tools, and marriage partners drifted apart. Mountains, deserts, oceans, and sheer distance broke networks that had once tied everyone together. Isolation is dangerous. A small group cut off from others can be wiped out by a single unlucky event, or slowly eroded by inbreeding and lack of new ideas. But isolation also creates space for uniqueness. On different continents, under different skies, human groups began developing their own distinct tool traditions, rituals, and ways of organizing society. In Europe, some populations created finely worked blade tools, and later, the stunning cave art that would captivate archaeologists tens of thousands of years later. In Southeast Asia and Australia, people learned to manage fire on a landscape scale, transforming forests and grasslands, shaping ecosystems in subtle ways. In the Arctic, others perfected clothing and dwelling designs that made survival in sub-zero temperatures not just possible, but reliable. Each region became a workshop of local solutions. Some ideas never spread beyond a valley or an island chain. Others slowly radiated outward, jumping from group to group over centuries, blending with whatever they met. This patchwork of isolation and contact, separation and reconnection, is what turned human culture from a single thread into a woven tapestry. When you zoom out and look at this period, roughly 70,000 to 50,000 years ago, and the tens of thousands of years that followed, it can be tempting to focus only on the big patterns, population expansions, genetic signatures, tool industries, migration routes. But underneath all of that were individual decisions, individual emotions, fear at the edge of a desert you've never crossed before, relief when you find a spring on the other side, awe the first time you see mountains taller than any cloud you've known, grief when someone dies far from the home they were born in, quiet pride when a tool you invented yourself saves someone's life. We often talk about the courage of explorers as if it's a rare thing, but for tens of thousands of years it was normal. Simply to be human meant living with the possibility that tomorrow your group might pack up and walk toward a horizon no one you knew had ever seen. Curiosity wasn't a luxury, it was a survival trait. The people who noticed a faint glow of land beyond the waves at low tide, the ones who wondered, what's over that ridge? The ones who stayed awake a little longer at the campfire, tracing constellations and using them to orient themselves. Those were the ones whose descendants would populate new continents. We inherit their world, but we also inherit their minds, their restlessness, their pattern-seeking, their strange mixture of caution and daring. By the time humans had reached Australia, crossed into the Americas, and scattered across Eurasia, something irreversible had happened. Migration had braided together genes, ideas, and environments into a single, global experiment. Innovation wasn't just happening in one place anymore. It was happening everywhere, all at once, in endless variations. The bottleneck had forged a species ready to adapt. The Great Dispersal gave that species the stage it needed. The result was an acceleration of change unlike anything earlier hominins had experienced. Tools, social systems, symbolic behavior, and eventually art and ritual all began to flower in ways that would have been unimaginable to those first survivors huddling in African refuges during the Great Dying. And yet, even with all this movement, all this change, one thing remained constant. The same fused chromosome, the same core genetic toolkit, the same basic brain architecture, refined by crisis and unleashed by opportunity. From here, the pace of our story will only quicken. The innovations sparked by migration, will feed into language, art, and the complex social worlds that define what it means to be human. The world was no longer just a place to survive, it was becoming a canvas, and our ancestors, scattered now from equator to ice, were just starting to learn how to paint on it. The acceleration didn't stop with that first meeting on the shores of the Arabian Peninsula. If anything, that was just the warm-up. From there, the story speeds up. For hundreds of thousands of years, change had been measured in tiny increments. A slightly better stone point here, a new hunting strategy there. But once behaviourally modern humans were fully awake, once language, symbolism, and complex social networks were in place, evolution gained a new engine: culture. Instead of waiting for random mutations to spread slowly through populations, ideas could leap from mind to mind in a single conversation. A new way of making a tool, a better way to share food, a clever hunting trick. All of it could spread across entire regions in a few generations, and then, much later, humanity triggered the next massive phase shift, the Neolithic Revolution. Imagine you're one of those descendants of the bottleneck survivors 12,000 years ago. Your people are still living by foraging, hunting, and gathering, just as humans had done for almost all of our history. You follow the seasons, track the migrations, know every plant and animal in your range. Life is mobile, flexible, and precarious. Then someone notices something small. Maybe a child drops seeds near a campsite, and months later finds a patch of familiar plants growing thicker than usual. Maybe an elder watches wild grain fall from its stalks and realizes that the plants come back each year in the same place. Gradually a thought begins to form. What if we don't just gather food? What if we grow it? This idea didn't appear in one place at one time. Evidence suggests it emerged independently in multiple regions. The Fertile Crescent of the Middle East, the valleys of China, the highlands of New Guinea, the forests of West Africa, the Americas. Each case, a variation on the same pattern, humans turning their minds, sharpened by 100,000 years of survival, towards shaping the environment itself. Agriculture was the next great leap. Instead of following food, food would now follow us. Instead of living entirely at the mercy of wild herds and seasonal berries, we could plant, water, weed, and harvest. But this came with a cost. Settling down meant vulnerability. Fields could fail, droughts could devastate entire villages, stored grain attracted pests and people. Inequality began to appear more starkly, as some families controlled more land or more harvest than others. Diseases adapted to higher population densities, hierarchies solidified. Yet for all its downsides, agriculture did one thing that mattered profoundly for the story of acceleration. It allowed more people to live in one place for longer periods of time. More people meant more minds feeding into the collective problem-solving engine. More children surviving to adulthood meant more continuity of knowledge. Larger communities could support specialists, people who didn't have to hunt or farm all day, who could instead focus on tools, weaving, healing, rituals, stories. Once people began to gather in permanent settlements, another threshold appeared on the horizon: cities. At first they were barely more than oversized villages, clusters of mud brick houses, a central storage building, a shrine. But as centuries passed, they grew. Walls rose, marketplaces formed. Labour could be organised on a scale no small band could ever manage. Canals were dug, fields irrigated, forests cleared. Temples and monuments lifted stone into the sky. And with cities came a new problem. How do you keep track of everything? Grain stores, trade agreements, taxes, laws, genealogies, religious rituals. Suddenly memory and spoken language weren't enough. Oral tradition, however refined, had limits. So humans did what they'd been doing since the bottleneck. They invented a tool to extend their minds: writing. The earliest writing systems we know of often began as accounting devices. Small marks on clay tablets in Mesopotamia, carved symbols on bone and shell in ancient China, tally systems, knotted cords, pictographs turning into abstract signs. At first, they were simple: numbers, goods, names. But once the idea exists that sound can be mapped to symbol, that speech can be frozen in space and time, everything changes. History can be preserved. Laws can outlive the rulers who declared them. Stories can travel beyond the reach of any one storyteller's voice. If language was a revolution inside the mind, writing was a revolution outside it. It created a second environment for evolution, the world of information. Ideas were no longer limited to what individuals could personally remember or physically teach. They could be stored, copied, and passed down through generations that might never meet. And like genes in a population, written ideas could mutate and recombine. Philosophy, mathematics, astronomy, literature, entire civilizations refining concepts across centuries. Cultural evolution, already fast, became exponential. Think about the timeline. For millions of years, stone tools changed slowly. A new design might take tens or hundreds of thousands of years to spread. After the bottleneck and the rise of behavioral modernity, toolkits could shift noticeably within a few thousand years. After cities and writing, major conceptual advances, new religions, scientific theories, political systems could spread across continents within centuries. Today, a new idea can circle the globe in hours. The tempo keeps increasing. Some scientists argue that even our genes are still riding this wave. The old picture of human evolution, slow, mostly finished long ago, is being replaced by something more dynamic. When researchers examine patterns of genetic variation in modern humans, they found signs that many gene variants have increased in frequency in just the last 10,000 years. Lactose tolerance in dairying populations, changes in skin pigmentation in response to new latitudes, immunity adaptations in response to crowded agriculture-based diseases. Even some brain-related genes show evidence of recent selection, though what exactly they do is still debated. We didn't stop evolving when we left Africa, or when we invented farming, or when we built cities. Evolution simply changed gears. Biological evolution continued, but cultural evolution started to move much faster. And as culture transformed our environments, diet, disease, social structure, it created new selection pressures, feeding back into biology. Our ancestors shaped the world in turn shaped them. Now, in the last few centuries, another shift, the digital age. On the surface, smartphones and satellites may seem disconnected from the stone tools of Africa or the rituals of Neanderthals. But in a deeper sense, they're part of the same trajectory that began when small groups huddled around fires, telling stories and teaching each other. The key pattern is this: we keep building external systems to store, transmit, and transform information. At first, those systems were memories and myths, then art on cave walls, beads and carved symbols, then clay tablets and papyrus, books and libraries, then printing presses, telegraphs, radios and televisions. Now servers hum quietly in distant data centers, holding more information than any ancient city could have imagined. Algorithms route knowledge, filter it, amplify it, bury it. What used to be a few dozen voices around a campfire has become billions of voices connected in real time. The same traits that helped bottleneck survivors coordinate hunts and remember seasonal patterns, language, social intuition, pattern recognition, are now applied to decoding online signals, navigating social media, adapting to a world where information itself is the main resource. Some researchers even talk about a global brain, a network of humans and machines, sharing data at speeds that dwarf anything in our evolutionary past. Whether or not that metaphor is literally true, the underlying reality is clear. The compounding of knowledge has never been faster, and this, more than any single mutation or invention, might be what makes humans unique. Other animals learn, other animals use tools, some even teach their young. But humans stack ideas on top of each other across generations with hardly any reset. A hunter 50,000 years ago could learn to make a spear point in a single afternoon, but that design was the product of countless small innovations by ancestors stretching back beyond memory. You, right now, living in the digital world, are using technologies that depend on mathematics invented in ancient Mesopotamia, geometry refined in Greece, paper from China, printing from Europe, electricity theories from the 19th century, semiconductor physics from the 20th. Every device, every building, every word on your screen is a layer cake of accumulated insights. Each generation doesn't start from zero. We begin where the last one left off. That's the real acceleration. Knowledge compounds. A small improvement in how we share information, like language, sets off a chain reaction. A small improvement in how we store information, like writing, pushes that reaction further. A small improvement in how we link minds together, like the internet, makes the whole system even more explosive. But this raises a quiet, unsettling question. Where is this acceleration taking us? Our ancestors at the bottleneck couldn't have imagined agriculture. Early farmers couldn't have imagined satellites. We, sitting inside our own moment, can barely glimpse what might come next. Some thinkers imagine futures where humans merge more tightly with machines, neural interfaces, artificial intelligence woven into daily life, biological limits pushed and blurred. Others imagine a different kind of change, social transformations, new ways of organizing communities, new ethics for a world where every action can ripple globally. There are darker possibilities too. Environmental collapse, technological misuse, new forms of conflict amplified by powerful tools. From the perspective of deep time, all these possibilities are like branches on a tree whose trunk was formed in that ancient crisis 900,000 years ago. The bottleneck, the rise of language, the invention of agriculture, the birth of cities, the digital web of today, they're all connected stages in one long experiment. An experiment in what happens when a species evolves, not just to survive, but to remember, to model the world in symbols, to pass those symbols forward, to build on them. As you lie here listening, you are part of that experiment. Every thought you have, every story you hear, every bit of knowledge you pass on, however small, becomes a thread in the fabric of human culture. Most threads will vanish unnoticed. Some will tangle. A few will guide the next turn of the path. But all of them rest on the same foundation, a spark of adaptability ignited in desperate times. Your ancestors stood on African plains watching storms they couldn't control. They tracked the stars, the seasons, the movements of animals. They whispered lessons to their children by the flicker of firelight, the way we now whisper lessons through glowing screens. They had no idea where their tiny innovations would lead. Agriculture, cities, writing, science, the digital cloud. None of it was planned from the start. It unfolded because a species, once nearly erased, turned out to be very, very good at learning and at remembering. So, as the acceleration continues, as ideas multiply and futures branch, one thing remains constant. You are the inheritor of that ancient spark. The same instincts that helped a small band survive the Great Dying now help you navigate a world of information storms instead of sandstorms, data floods instead of monsoon rains. The pace is faster, the tools are stranger. But the mind at the center, curious, anxious, hopeful, endlessly seeking patterns, is recognizably the same. When you close your eyes later, imagine the long chain behind you. Tiny groups hiding in refuges, bands of foragers tracing rivers, early farmers pressing seeds into soil, scribes leaning over clay, scientists scribbling equations, engineers wiring circuits, programmers typing lines of code, and then you, listening, breathing, resting at the far edge of a story still in motion. Whatever comes next, however the acceleration continues, you are part of a lineage that has been facing the unknown for almost 1,000,000 years, always adapting, always imagining, always carrying the fire forward into the dark. So now, as the noise of the ice ages fades, and the last migrations slow in your imagination, you're left with a strange realization. There was no single switch. No one moment when a lonely child in Africa suddenly spoke the first true sentence. No single night when a group of hunters painted the first image on a cave wall and woke up modern. What happened around 100,000 years ago wasn't a miracle event. It was a convergence, climate chaos tightening and then loosening its grip. Tiny populations pushed to the edge, then released. Brains slowly rewired over hundreds of thousands of years, language emerging bit by bit, from gestures and grunts to shared stories and whispered plans. Trade routes like invisible threads, sewing small bands into larger networks. Art, ritual, burial, symbols, genes shifting, mutating, being tested under pressure no modern society has ever known. All of it happening at once, overlapping, reinforcing, accelerating. When you look back across that vast stretch of time, it's tempting to draw a neat line to say, here, this is when we became human. But the deeper you look, the fuzzier the line becomes. Every fossil, every stone tool, every scrap of ancient DNA tells part of the story, then trails off into silence. We can trace the outlines. We can run simulations, build timelines, argue about dates. We can say with some confidence that climate swings mattered, that language mattered, that social networks and symbolic thought and a few well-placed mutations all played their part. But beneath all of that, there's something we can't quite name, some quiet, stubborn spark that kept our ancestors experimenting when the wind was howling and the rivers were dry. That made them sit up late around the fire, napping stone just a little more carefully, telling stories just a little more clearly, teaching children not just how to survive but how to remember. Studying a past this deep demands a kind of humility that doesn't come easily to us. Our species loves certainty. We like clean answers, final explanations, tidy endings. But deep time doesn't care about our need for closure. The farther back we look, the more we're forced to live with maybes and almosts and could-have-beens. Maybe language began earlier than we think. Maybe art arose independently in multiple places and then vanished, leaving no trace. Maybe some brilliant innovation flared briefly in a tiny group that died out, its ideas lost to erosion and chance. We will never know all of it, and that's okay. Because part of the beauty of this story is precisely what we can't pin down. The gaps remind us that we are small, that our knowledge, impressive as it feels, is just a thin film on the surface of something unimaginably deep. Yet you are connected to that depth in a very literal way. Every cell in your body carries echoes of those bottleneck survivors, of Neanderthals in frozen valleys, of Denisovans on mountain passes and distant islands. Their struggles shaped your nervous system. Their fears and hopes shape the architecture of your mind. The way you think, dream, love, remember, none of it is an accident. It is the outcome of a long, fragile chain of survival, stretching back through unbroken night. So as you lie here, listening, somewhere on a small planet spinning through space, you're not separate from this story. You're the latest chapter. If you'd like to stay with this journey, through more forgotten ages, more half-buried mysteries, you can gently support it. You can like this video so others can find it. You can subscribe if you want more long, slow explorations to fall asleep to. And if you feel like sharing a tiny piece of your own story, you can let us know in the comments where in the world you're listening from tonight. A quiet map of modern humans, scattered across the globe, connecting again, this time through a screen instead of a trade route. If you'd like to go a step further, there's also an optional channel membership here on YouTube. It's never expected, but it does help us keep making these deep dives into the past, with the time and care they deserve, only if it feels right for you. For now, though, you don't have to do anything. Just imagine the sky above you, wherever you are. City glow, country dark, storm clouds, or clear night. It doesn't really matter. Above all of that, beyond the light and the weather and the noise of modern life, the same stars are still shining. The same constellations our ancestors watched from African savannas, from ice-rimmed caves, from forest clearings and windswept coasts. They looked up at those pinpoints of light with questions they could never fully answer. You're looking up at the same lights, carrying the same unanswered questions forward. Let them hang there for a while. Let the mystery rest around you like a blanket. The journey for tonight is complete.